Hey there. Welcome back to Calculus. In this video lecture, we're going to start our work in chapter 4, which is a very cool chapter with lots of interesting applications of the derivative. And in particular, in section 4.1, we're going to see how you can use differential calculus to find maximum and minimum values of functions, optimizing functions. It's an important problem in all kinds of science. Usually, if you're interested in some function, you're interested in what its biggest and smallest outputs can be and where those outputs happen. Yeah. So if you're a physicist, you might be interested in like what the maximum velocity of something is going to be, the minimum velocity. Maybe you're an economist and you're looking at your revenue function. People usually want to maximize that revenue function or minimize the cost function and so on. So there's all kinds of places where finding minimums and maximum values is a useful skill. So we're going to look at a little bit of the details of how to do that in this first section. So let's walk through the objectives. You can see it's kind of a busy agenda. I'm going to move through a lot of this theory and do a couple of examples in this video, and then I think I might just make a short video where I try to produce 2 or 3 more examples to give you variations on different kinds of functions, polynomials, trig functions, and so on. But so what are we going to do? We're going to make a couple definitions. I want to tell you about the difference between what I mean by an absolute versus a local minimum or maximum value. All right, so there's a couple of different flavors of these things. I want to show you how to locate them. I want to be able to find absolute and local minimums and maximums on a graph. Then I'm going to state without proof a kind of fundamental theorem in this business called the extreme value theorem. It says continuous functions on closed intervals always have these global maximums and mins. Fermat's theorem is a result about where to look for them. So we'll state that a little bit later down. And then in particular, we're going to just give a name for where we look for these things, these critical numbers. I want to show you how to find them. And then summarizing it all in this, what the book calls the closed interval method to locate the absolute minimum and maximum values for a continuous function on a closed interval. Okay, so that's our agenda. Busy agenda. Let's get going. Got a couple of definitions from our text here and an accompanying picture I drew to warm us up to them. So what do we mean by these minimum and maximum? Well, I'm assuming you have some intuitive notion for what minimum and maximum means. Maximum being largest value, minimum being smallest. But what about this absolute versus local? So I'm just going to kind of use this picture as we look at them. Say, for example, if I look at this y value at this point C1, I'll just highlight the point with the laser pointer here. The y value there, that y value is not the smallest y value on the graph. Yeah, so it is not an absolute minimum. That's not an absolute minimum value. There's no absolute minimum. But if you stayed near x values close to C1, that is the smallest y value on the graph there. Yeah. So that's what this notion of local minimum means. A local minimum is a function value that's, well, less than or equal to other function values, but only nearby. So again, I think looking at this point C1 over here, it's a nice way to visualize what I mean by a local minimum. There are y values on the graph that are smaller than that f of C1. But if you stay near C1, f of C1 is the smaller than or equal to the y values that are nearby it. So it's a local minimum, right? There's another local minimum over here at C3. There's another local minimum over here at C3, staying near the values of x near C3, that f of C3 is going to be less than or equal to anything else in that neighborhood. C3, actually, f of C3 happens to be the smallest y value on the entire graph. That's what we mean when we call it an absolute minimum. Sometimes in other books, and you'll probably hear me because in the school I grew up in, we call these things global. Global is a synonym for absolute minimum. A global minimum just means that your y value is literally less than or equal to any other y value on the entire graph. And we always speak about the entire graph. I mean, whatever the domain of the function is, right? Now, these arrows that I've drawn here kind of indicate that this function's domain is the entire real line. The picture just continues indefinitely. So to kind of summarize what we were just saying there, we have local minimum values at, say, f of C1 and f of C3. Yeah, we have a global minimum value at f of C3, global or absolute. See, there I go doing it. Global minimum value at f of C3. And we won't belabor this that much for maximums. Maximums is the same idea, but we're just talking about the other inequality, bigger than or equal to things. So you can see that the y value f of C2 is greater than or equal to any other y value near it. Yeah. So we have a local maximum value at f of C2. There is no global maximum on this thing. Again, that's what these arrows indicate. This function's values will just increase without bound. So let's write that we've got a local maximum value f of C2. I shouldn't say at here, sorry, because the value is the output coordinate. So local minimum values colon f of C1 and C3, global minimum value f of C3, local minimum value f of C2. There is no global maximum value for this function. Okay, so I hope that that example helps illustrate what these ideas are. All right, let's look at an example. Took this example from your text as well. It's a fourth degree polynomial there. And the point I want to emphasize is the domain part, all right? So this function is defined only for values of x between -1 and 4. So notice there are no arrows on the graph indicating that something is increasing without bound. Those are the endpoints. So we're only considering values of x starting at -1 up to 4. That's the domain of this function. So let's just look at the function and list some local minimum values. We can kind of identify them with the laser pointer first. It looks like f of 0 is a local minimum value. F of 3 is a local minimum value, and I don't see any others. So the two local minimum values would be f of 0 and f of 3. You can also say there's local minimums at x equals 0 and x equals 3. So in particular, when the author is using the word value, they mean he means outputs. Okay, and me too. When I say local minimum value, I mean outputs. If I say a local minimum, I would be talking about the input there. All right, how about global? Global minimum values, it looks like f of 3. F of 3 over here is the smallest y coordinate on that graph, period. See any local maximum values? There's certainly here one at f of 1. There's one there at f of 1. What about over here at -1, f of -1? It's certainly a maximum value. No y coordinate on that graph is bigger than it. The author of the book won't call that a local max value because it's an endpoint. All right, so for a local maximum, you have to have values of x near that input, and in particular, you have to be able to be near that input on both sides. So there's just one local maximum value with our book's terminology here, and it's at f of 1. The global max value is at f of -1. F of -1 is a global max value. F of -1 is greater than or equal to any other y coordinate on that curve. Notice over here at 4, f of 4 is neither a local nor global minimum or maximum. All right, it's not local because it's an endpoint, and it's not a global maximum, well, because there are y coordinates on the graph that are bigger than that y coordinate. Cool. All right. So just some more practicing with the terminology, local versus global, minimums, maximums. If you want to talk about minimums and maximums at the same time and your tongue starts getting tripped up, you can also use the word extrema. So extrema means either a minimum or a maximum. So you can talk about local extrema, global extrema, absolute extrema. Okay. All right. So here is kind of the fundamental result of this business. We won't prove it. Proving it would require a little bit more mathematical rigor machinery than we have, but we're just going to state it, and I'll try to give you kind of an intuitive idea of why it's true. I've got 3 pictures here anyway, but what is the theorem saying? If you take, let's just kind of highlight the hypotheses. If you take a continuous function, it's important that this function is continuous on a closed interval. Okay, so remember those brackets mean that the value of a and b are in there. This didn't render very well. Let me emphasize that a and b are both in this domain. Okay, so a continuous function on a closed interval will always have an absolute maximum value, f of c, and it'll always have an absolute minimum value. It might have more than one, but it at least has one absolute maximum and one absolute minimum on the interval from A to B. So your author is showing you three pictures down here. Let's just kind of look at them one at a time. Here's a continuous function on a closed interval. It looks like it has an absolute maximum at C and an absolute minimum at D, and those things look like they are unique. Yeah. This one has an absolute minimum in the interior. Maximum. The absolute minimum is an endpoint. That's okay. D can be an endpoint. In the third example over here, the author is showing us, look, there's more than one absolute maximum, both C1 and C2. There's one absolute minimum. In general, you can have as many, there's no limit on them. But the extreme value theorem says that there's always at least one of each kind. So you could probably stop this video. I think this would be kind of a fun exercise. Stop the video and try to draw a continuous function on an interval from A to B that doesn't have one. You can't do it. If I kind of ruin this picture by, say, starting right there and trying to draw a new function, right? It has to be continuous. So I have to get all the way over to B, and I am not allowed to have any jump discontinuities or anything like that. I can have sharp bends. Yeah, it can wiggle. It has to be continuous, though. I can't have any jump discontinuities. I can't have any asymptotes. At some point, my pen had a highest Y value. It had a lowest Y value. It has to. So stop the video and play around a little bit. Try to foil the theorem. Maybe you could become famous if you could draw a continuous function on a closed interval that doesn't have an absolute minimum or an absolute maximum, then you'll be famous. The next couple of pictures I want to show you just emphasize that these two hypotheses, continuous and closed interval, are necessary, in that if you took either one of them away, you can have functions that don't have those extrema. So looking at, say, this figure 9 first, this function's not continuous. You can see it's got a jump discontinuity. It's not a continuous function, and it doesn't have a maximum value on that interval. So pause the video and make sure that makes sense. If you're looking at this saying, well, the maximum value is 3, that little open circle means the function's outputs never get to 3. Yeah. So it looks like it's the input 1. So if we use some of our old language, it certainly is the case that the limit, as this input variable is called x, approaches 1 from the left of f of x is 3. That's certainly true, but f of x doesn't equal 3 for any x. So that's why there's no absolute maximum. The function's values get as close to 3 as you like, but they never get there. So that discontinuity is allowing for this function to not have a maximum value. Its global minimum value is at x equals 2. It's 0. Over here, what's this function on the right? It's continuous, but the interval's not closed. What do I mean by that? There's no endpoints. So that's a continuous function, and it has no minimum value. Yeah, the y coordinates are approaching 1, but they never get there. That's what that open circle means. It clearly has no maximum value. The y coordinates on this function are growing without bound. Okay, so both ingredients are necessary, but if you have a continuous function defined on a closed interval, then you can always find a global, it has to have global minimum and maximum values. All right, so before we move on, I just want to kind of notice something about anytime you have one of these extrema, a global minimum or maximum that's not an endpoint. What can you notice about the tangent line there? At that global maximum, if I drew a little piece of the tangent line, it's horizontal. At this global maximum, that piece of the tangent line is horizontal. It always is. In the case that the function is differentiable, at any one of its interior extrema, local mins or maxes, the tangent line has to be flat. All right, that's kind of an interesting observation, and it's going to be a tool that we're going to use because, again, we're interested in finding the locations of these extrema, right? Maybe without looking at a picture, maybe we don't always have a graph. Well, that's kind of a key insight, that it looks like at these extrema, tangent lines are 0. So that is the statement of what is called Fermat's theorem. And I'm going to sketch a little bit of a proof here. I wrote it out so I can kind of go faster. But Fermat's theorem says that if you have a differentiable function, the author meant that. They didn't state it here explicitly. Oh yeah, they did. They did. The author stated it right here. And f prime of c exists. So if you have a function that's differentiable at a point c, and it has either a local minimum or a maximum, it doesn't matter which one, at c, then the derivative at c would have to be 0. That's what I was just noticing. Sorry, I'm gonna scroll back up and look at these pictures again, but that's what I was noticing, is that the derivative is 0 at any place that you have an extrema when the derivative exists. All right, so this is called Fermat's theorem. Let's just really quickly kind of walk through the proof of it here. It's for local minimums or maximums. You have to kind of do two cases. I'm going to suppose that we have a local maximum. So suppose that f of c is greater than or equal to any other value on the graph, nearby anyway, and that f is differentiable. So we're looking at the difference quotient definition, f prime of c, it's the limit of this difference quotient. And then what I want to emphasize is that if c is a local maximum, f of c is a local maximum value, well then f of c plus h has to be less than or equal to it. So if you subtract f of c plus h minus f of c in that order, you have to get something that's less than or equal to 0. Yeah, that's because this number is guaranteed to be greater than or equal to this one. And when you subtract a bigger quantity from a smaller quantity, you can't get a positive number. All right? So now looking at the difference quotient, if we look back at this difference quotient, what I was just saying is that its numerator is negative. Its numerator is negative. So if h is a small positive number, you divide a negative number by a positive number and you get a negative number, right? So then taking the limit as h goes to 0 from the right, we'd have to get the derivative. That limit has to exist from the right and left and equal to two-sided limit. And if you're taking a limit of things that are all less than or equal to 0, the limit has to be less than or equal to 0. So that's my proof of that f prime of c has to be less than or equal to 0. But we also have to take the limit as h goes to 0 from the left, right? It's a two-sided limit. And there we're taking a negative number and dividing it by a negative number. Well, that's going to produce a positive result. And again, if your quantity is greater than or equal to 0 for every value of h less than 0, and you take the limit as h goes to 0 from the left, that limit would have to be greater than or equal to 0. Well, there's only one number that's greater than or equal to 0 and less than or equal to 0, and that number is 0 itself. All right, so there's our little sketch of a proof of Fermat's theorem. All right, so we're interested in finding these extrema. We think we have a hint. We should look where the derivative is 0, but we should be a little bit careful. All right, I have kind of just one cautionary tale here. To find extrema, we're going to look for values that satisfy f prime of c equals 0. That's what Fermat's theorem says, that if you have an extrema, that's going to be true if the derivative exists. But we need to be a little bit careful because sometimes you have one of these numbers that makes the derivative 0, but you don't get an extrema there at all. Yeah, if we looked at the tangent line to this cubic function at x equals 0, that tangent line is certainly flat, but there's no extrema there, right? The f of 0 is not a minimum value, it's not a maximum value for the cubic function. It's doing neither. Conversely, or not conversely, but additionally, you can have extrema at places where derivatives don't even exist. Look at the absolute value function over here. If you look at the absolute value function, it certainly has a global minimum value, f of 0. It's 0. It's the global minimum value is 0, and it happens when c is 0, the input is 0, but the derivative doesn't even exist there. Yeah, so if we only looked for places where the derivative was 0, we wouldn't find this one. We wouldn't find this one. But it turns out that if you look for places where this derivative is 0 or undefined, then you would have a complete list of where the possible extrema could happen. I say possible extrema because you don't always get one, but you'd have a finite list of places where you can look. Okay, so that's our next fact, or definition rather. I'm just going to give a name. We're going to call a value, an input value, a critical number. So a critical number of a function is a number that makes the derivative either 0 or the derivative doesn't exist. Most people don't do this, but I do. I call the first kind good critical numbers. They make the derivative 0. I call the second kind bad critical numbers. I know it's judgmental. I shouldn't do it. But so critical numbers come in two flavors, good and bad. Good critical numbers make the derivative 0. Bad critical numbers, the derivative doesn't exist. And Fermat's theorem is basically telling us if you're going to go looking for extrema of functions, you should look at the critical numbers. All right, let's do a quick example where we find them all. Let's find all the critical numbers for this algebraic function there, f of x. You can see it 3 times x to the 4/3 minus 6 times x to the 1/3. All right, so let me show you the procedure. When you're finding all the critical numbers, you step one, take the derivative. Calculate f prime of x. All right, it's power rule. F prime of x is 3 times 4/3 x to the, you have to subtract 1, so that's 1/3. And then it's 6 times 1/3, subtract 1 from 1/3, and you get negative 2/3. All right, so if we clean up the coefficients here a little bit, that's 4 x to the 1/3 minus 2 x to the negative 2/3. Okay, and now, so I'm done differentiating, but I need to answer a couple of questions about this derivative. I need to know, when is it 0, when is it undefined? And this form is not all that useful for answering that. So I'm going to put it in a form where I can answer that. I'm going to factor out the two exponents that I have here, 1/3 and minus 2/3. You can always factor out the smaller one. The smaller exponent is minus 2/3. So I'm going to pull that out of this expression. So I'd have 4, when you factor negative 2/3, x to the negative 2/3 out of x to the 1/3, you get x to the 1. And I factored it completely out of that other term, so it would be times 4x minus 2. All right, I could have also factored out a 2. Maybe I'll do that on the next line. So if I do that, factoring a 2 out of 4x minus 2, it's 2 times 2x minus 1. And I'm going to write that negative exponent. So you might be wondering, watching me do this, like, why? Why are you doing that algebra? Well, now I've got this in a form where it's easy to answer our two questions. Yeah, one of the things I want to know is, where's the derivative equal to 0? This is a super important fact. Fractions can be 0 only when their numerators are. So can you stop for a second and look at that expression in the numerator and tell me the values of x that make that 0? Yeah, and then I also need to know where it's not defined. Well, fractions are undefined only if their denominators are 0 and their numerators aren't. So that's why I wanted it in this form, okay? So I can say, I'm gonna have to scroll here a little bit. I can say that f prime of x is 0 if and only if is what that little symbol means. The numerator is 0. Right? And you can certainly divide both sides of that by 2 and then add 1 to both sides. So that's going to be if and only if 2x is equal to 1. That's if and only if x is a half. There's one good critical number. It's x equals a half. F prime is undefined. I'm going to use our acronym doesn't exist if and only if the denominator is 0. Well, the 2/3 power of x is 0 if and only if x is 0. So this function has two critical values. Two critical values. What are they? X equals a half and x equals 0. All right. One of those critical values is good, makes the derivative 0. One of them is bad, makes the derivative undefined. Fermat's theorem, or a slightly generalized version of it, is telling us that if we're going to look for extrema of this function, we should look at those places. We should look at those places, because if you're going to have an extrema there, it's going to have to be a critical value. All right, so you're going to have a whole bunch of homework problems where it's asking you to find these critical values. Okay, so we're going to look at one more kind of topic here, and I'm going to do one more example, and then I'm going to cut this video off and probably do, I would say, 2 or 3 more examples to illustrate this closed interval method, but I'll do it in a second video so that this one doesn't get too long. So the main problem in this section, in the homework that I'm going to ask you to do, is the following. I'm going to ask you, given a continuous function on a closed interval, I'd like you to be able to find its global minimums and maximum values. All right, so how do we do that? It's kind of a procedure. It's a step-by-step procedure. You can look at the steps here. I'll just read them with you, and then we'll implement them in this example. So you begin by finding all the critical numbers of your function that are in the interior of the interval. Yeah, so you have to find all the critical values that are between a and b strictly. And then you evaluate your function at any of those places. You also have to evaluate your function at the endpoints of the interval, because as we saw above, in that 4th degree polynomial, you can have an extrema, it was an absolute maximum, if I recall correctly, at a place where the derivative isn't 0, just because it gets cut off. If the domain is a closed interval, the endpoints can give you extrema. All right, so we'll just find all the critical values and table them together with the endpoints, look at all the function values, and we'll be able to see which one's biggest and which one's smallest. Okay, so let's do it. In this example, this is the same function that we just found all the critical values for. So to save us a little bit of time in this example, I'm just going to recall to us that f prime, we worked this out above. Maybe I should look at it. I'm going to try to do it from memory. It was 2 times 2x minus 1 over x to the 2/3. Okay, so there were 2 critical values. I won't recapitulate finding them. 2 critical values in the interval from -1 to 1. They were x equals 0 and x equals 1/2. Yeah, both of those values are in the interval from -1 to 1. Okay, so then I like to make a table to organize my information like this. I hope I can talk you into making it too. What am I talking about making a table? I'm going to make a table of input and output values. And in this table, I always put any and all critical values that I found. So we did that work above. Yeah, so I always list these things, good and bad, critical numbers, critical values. All right, and then you also have to list the endpoints of the interval, always. So this table will always minimally have 2 numbers for inputs, the 2 endpoints. Could have more if there are critical values that are interior. All right, and then what do? You evaluate f, not f prime, but f. Yeah, you evaluate f at those 4, in this case, 4 numbers, and then we'll be able to see where the largest output and the smallest output are. All right, so I'm gonna just fill them in and let you check this arithmetic later. I don't want to keep this or make this video too long, but if you but it's important. I'm not plugging these into the derivative. I'm plugging them into the function. Yeah, because I'm looking for its output values, not the derivative. So if you evaluate f at 0, you'll get 0. If you evaluate f at 1/2, you'll get, as a decimal, approximately -3.5. I'm rounding. All right. If you evaluate at 1, you'll get -3. And if you evaluate at -1, you'll get 9. All right. So now looking at those 4 outputs, you can see which one is the smallest and which one is the biggest. Yeah. The maximum value, that's a absolute global maximum value, is 9. It happens at x equals -1. All right, where's the minimum value? Which of those 4 numbers is the smallest? Can you say? -3.5. It's an absolute minimum value. It happens when x is 1/2. All right, so I've got a Desmos window ready. I'm going to switch over to it, and we're going to look at what we just did graphically. I want you to always be looking at these things graphically, and then I'm going to stop this video, and I'll make a second short one with, I don't know, 2 or 3 more examples. All right, but let me find my window switcher here. All ready to go. I think you can see Desmos. So what are you looking at a graph of? You're looking at a graph of our function, our 3 times x to the 4/3 minus 6 times x to the 1/3. Here, I can show it to you if you want to see in the Desmos window there. I've plotted this thing. It was between -1 and 1. I made it a little bit wider because I like to be able to see. But remember, our endpoint here was -1 to 1. So we're only looking at the function there. And well, what do you think? What did we say? We said that the absolute maximum was happening over there at -1. And although it's close, it's getting kind of cut off in the graph. That is definitely the biggest y coordinate on this graph between my x equals -1 and 1. It's happening over at -1. And we know what that y coordinate is. We calculated that it was 9. Right? So that's totally consistent. And then we said that our absolute minimum happened at the critical value x equals 1/2. Okay, so there's our x equals 1/2. I'll just motion the cursor down to be on top of the curve at the corresponding point. And that looks like the lowest y value on the graph to me. Yeah, we said that that was about -3.5. You can look at the scale in Desmos to verify that. All right, so that's the mathematics problem that we just did on the whiteboard before looking at a picture of this. Is we were able to locate the exact locations of those extrema. Check out this bad critical point. Can you see why it was bad? Why f prime of 0 doesn't exist? There's a vertical tangent line there. There's a vertical tangent line. So in this case, that bad critical point didn't give us an extrema. Sometimes they do, sometimes they don't. Okay, so I'm going to cut this one short. Thanks for listening, and come back and look at a few more examples. I'm just going to make a short video where we find the absolute minimums and maximums of some various functions on closed intervals. Okay, thanks.